Stand up right now. Seriously, stand up. Feel that? Your weight, your feet pressing into the floor, that heaviness dragging you down. You call it gravity, Earth pulling you toward its center. Simple, obvious, something you've understood since you were 5 years old, except it's wrong, not a little wrong, not needs a small correction, wrong. Fundamentally wrong about what is actually happening to you right this second. Because gravity isn't a force. It never was. And when you finally understand what gravity really is, and when you actually see it, the entire universe starts to look like a completely different place. Let me show you. Here's what school taught you. Objects with mass attract each other. Drop something, it falls. Moon orbits Earth. Planets circle the sun. Newton figured it all out 300 years ago with one elegant equation. Force equals g times mass, 1 times mass 2 over distance squared. Done. Gravity is a pull. Case closed. Except, think about it for a second. You're standing there right now feeling gravity. But what are you actually feeling? Not a pull. You're feeling the floor pushing up against the bottoms of your feet. That's the sensation. That's the only sensation. The floor pushing you upward. This mysterious downward pull that everyone talks about, you've never felt it. Not once in your entire life. You only ever feel the push. Always up, never down. So where exactly is this pull? And here's something even stranger. The moon is falling toward Earth right now. Has been for over 4 billion years. Falling and falling and falling, but it never gets any closer. It just circles endlessly. What kind of pull works like that? A pull that pulls forever but never actually pulls anything in? And according to Newton, that pull travels instantly. Move the Earth and the moon feels it immediately across 240,000 miles of empty vacuum. Instantaneously. No delay, no messenger, no mechanism. How? Newton himself couldn't explain it. He literally wrote, and I'm paraphrasing here, "I have not been able to discover the cause of gravity from phenomena, and I frame no hypotheses." He called it action at a distance and admitted it made no sense. But the math worked so beautifully, so perfectly, that people just stopped asking the uncomfortable questions. They shouldn't have. To understand why everything you've been told is wrong, we need to go back, way back, to a time when nobody understood how planets moved at all. Copernicus said planets orbit the sun. Fine. But how? What shapes do they trace? What rules do they follow? A Danish astronomer named Tycho Brahe decided to find out, not by theorizing, but by looking. He built the most precise observatory in the world and spent decades recording planetary positions. Night after night, year after year, measuring angles with brass instruments down to fractions of a degree, obsessive, meticulous, relentless. Because here's the thing about nature, you can't understand it by guessing. You have to measure carefully, precisely, write down exactly what you see. That's where real science begins, not with theories, with data. Tycho's data eventually reached a mathematician named Johannes Kepler, and Kepler had one goal: find the shape of planetary orbits. He tried circles first, obviously. Circles are clean, elegant, divine, and the predictions were close, really close. But Mars was off by 8 arc minutes. That's 8/60 of a degree, tiny, almost nothing. Most people would have shrugged and called it measurement error. But Kepler knew Tycho. That man did not make 8 arc-minute errors. His data was gospel. So Kepler did something extraordinary. He threw out his entire theory, years of work gone, and started over. After years more of brutal calculation, no computers, no calculators, just pen and paper and sheer stubbornness, he found it. Ellipses. Planets move in ellipses with the sun at one focus. And it matched Tycho's data perfectly. Beautiful, revolutionary. But it raised an even bigger question. Why ellipses? What force, what mechanism, what invisible hand bends planetary paths into these specific shapes? Meanwhile, in Italy, Galileo was doing something that looked almost embarrassingly simple. Rolling balls down ramps. Sounds trivial, but pay attention to what happens. Roll a ball down an incline. It speeds up. Let it roll onto a flat surface. It keeps going, doesn't stop immediately. It gradually slows and eventually stops. But why does it stop? Because of friction, air resistance, imperfections in the surface. Now imagine you could eliminate all of that. Perfect surface, no air, no friction. What would happen? The ball would roll forever. Same speed, same direction, forever. This was radical. For 2,000 years, since Aristotle, everyone believed that motion requires a continuous push, that things naturally come to rest, that stillness is the default state of the universe. Galileo said, no, that's exactly backwards. Motion is natural. An object moving in a straight line at constant speed needs no explanation. That's the default. What needs explanation is change. Slowing down, that's friction. Speeding up, that's a push. Changing direction, that's a sideways force. This is inertia, Newton's first law, and it creates a puzzle that would reshape everything. If objects naturally move in straight lines, why don't planets? Their paths bend. They curve continuously toward the sun. Something must be deflecting them every single instant. What? Isaac Newton saw it with stunning clarity. Planets want to go straight. That's inertia, but they curve. Something is continuously changing their direction. He called it gravity, a universal force of attraction between any two objects with mass. The force depends on two things: how much mass and how far apart. More mass, stronger pull. Greater distance, weaker pull. And it weakens specifically with the square of the distance. Double the distance, the force drops to a quarter. With this one principle, everything fell into place. Why ellipses? Because planets are simultaneously falling toward the sun and moving sideways. The combination of those two motions, inward fall and sideways velocity, traces an ellipse. Kepler's laws aren't separate rules. They emerge from Newton's one law plus inertia. Why does the moon orbit? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same force, same law, just at a different scale. And then Newton did something that was honestly one of the most beautiful calculations in the history of science. He figured out how much the moon's path deviates from a straight line each second, how much it falls toward Earth. Then he calculated how much objects fall on Earth's surface in 1 second. He accounted for the difference in distance. The moon is 60 times farther from Earth's center than we are. The numbers matched perfectly. The force pulling an apple off a tree is the exact same force holding the moon in orbit. Heaven and Earth, same physics, same law, same universe. From there, the dominoes kept falling. Ocean tides, the moon pulling Earth's water, Earth's equatorial bulge, it's spinning. Comets returning on schedule, elliptical orbits, Jupiter's moons appearing early sometimes and late other times. That led to the first measurement of the speed of light. Wobbles in Uranus's orbit. Astronomers predicted a hidden planet, Neptune, and found it exactly where the math said it should be. For 200 years, Newton's gravity was the crown jewel of science. It explained everything anyone could measure. But there was one thing it couldn't explain, and it's something so simple, so obvious, that most people never even think to ask about it. Drop a hammer and a feather in a vacuum. They hit the ground at the exact same time. The hammer is heavier, way heavier. Newton's law says gravity pulls it harder, much harder, so it should fall faster, but it doesn't. Why? Because the hammer also has more inertia. It resists acceleration more. And these two effects, the stronger gravitational pull and the greater resistance to acceleration, cancel each other out, not approximately, perfectly, to as many decimal places as anyone has ever measured. Every object in the universe falls at the same rate regardless of its mass. A bowling ball and a marble, a tank and a tennis ball, a feather and a freight train, all fall identically in vacuum. Newton's theory requires two separate properties of mass to explain this. Gravitational mass, how strongly something attracts other objects, and inertial mass, how much something resists being accelerated. Two completely different concepts, and yet they're always equal, always. For every substance, every material, every object ever tested to extraordinary precision. But why? Why should the attracting property of matter be exactly equal to the resisting acceleration property? They're conceptually unrelated. It's like discovering that every object's color is exactly proportional to its weight. You'd want an explanation. Newton had none. It was just a coincidence. A remarkable, perfect, beautiful coincidence that happened to make the math work. Einstein looked at that coincidence and asked the question that changed everything. What if it's not a coincidence? What if gravitational mass and inertial mass are the same because gravity and acceleration are the same thing? Here's the thought experiment that started it all. You're in a windowless room, no way to see outside. You feel your normal weight pressing you into the floor. Question, are you on Earth standing in a building, or are you in a rocket ship in deep empty space, accelerating upward at 9.8 meters per second squared? Can you tell the difference? Drop something. It falls to the floor. Both cases. Throw a ball sideways. It curves downward. Both cases. Stand on a scale, same reading. Both cases. There is no experiment you can perform inside that room to distinguish gravity from acceleration. None. Zero. They are completely, perfectly, absolutely indistinguishable. Einstein called this the equivalence principle. And he didn't treat it as a curiosity. He treated it as a clue. If you truly cannot tell gravity from acceleration, if no experiment in the universe can tell them apart, then maybe they are the same thing. And that leads somewhere mind-bending. If gravity and acceleration are the same, then objects in free fall aren't being acted on by any force at all. The falling apple, no force on it. The orbiting moon, no force on it. Astronauts floating in the space station, no force on them. They're all doing the most natural thing in the universe, following the straightest possible path through space and time. But here's the twist. Space and time aren't flat. They're curved. Mass warps them, bends them, distorts the geometry. The apple isn't being pulled to the ground. It's following a straight line, but through curved space-time. And in the curved space-time near Earth, a straight line points toward the center. You, standing on the ground right now, you're not being pulled down by gravity. You're trying to follow your natural path through curved space-time, a path that leads toward Earth's center. But the floor is in your way. The ground pushes you upward, preventing you from following that path. That's what you feel as weight. Not gravity pulling down, the floor pushing up, deflecting you from your natural trajectory. There's only one force acting on you right now, the floor pushing up. In Newton's picture, two forces, gravity pulling down, floor pushing up, balanced. In Einstein's picture, just one, the floor pushing you away from where space-time wants you to go. And if there's only one force, and it's pushing up, then you are accelerating upward constantly right now. The falling apple isn't accelerating. The apple is free, finally moving naturally. You, standing still, are the one being forced. Standing requires force. Falling is the natural state. That's Einstein's revolution. And it's not just philosophy, it's measurable. Einstein made a concrete prediction. If gravity is curved space-time, then light should bend near massive objects. Light has no mass. Newton's gravity shouldn't affect it at all. But if space itself is curved, light following the straightest path through that curved space will bend. In 1919, during a solar eclipse, Arthur Eddington measured the positions of stars near the sun's edge. The stars appeared shifted from their true positions. The starlight had curved, passing through the sun's warped space-time, exactly as Einstein predicted, and that was 1919. Since then, we've confirmed it thousands of times. Gravitational lensing, massive galaxies bending light from objects behind them, is observed routinely. GPS satellites have to correct for time running faster in weaker gravity, or your position would drift by kilometers per day. Gravitational waves, literal ripples in the fabric of space-time, were detected in 2015, 100 years after Einstein predicted them. Black holes, neutron stars, the expansion of the universe, Mercury's orbital precession, a tiny anomaly Newton couldn't explain that Einstein's equations nail perfectly. All of it flows from one idea. Mass tells space-time how to curve. Curved space-time tells objects how to move. So the next time you step on a scale, remember, You're not measuring a downward pull. You're measuring how hard the scale has to push to stop you from following the natural geometry of the universe. When you watch something fall, you're watching an object finally set free. Free to follow the path that mass has woven into the fabric of reality. When you look at the moon, you're seeing an object tracing the straightest possible line through curved space, a line that looks like a circle because space itself is bent. Gravity isn't a force, it's geometry, the shape of the universe itself, and that is far more beautiful than any mysterious pull could ever be.